All right, we're going to go ahead and get started now. Welcome everyone to this webinar on power of metadata hydration for enhancing your AI testing. My name is Skip Everling. I'm the head of developer relations here at Kolena. And we've got Saad Hossain here from our machine learning engineering and research team. We're hoping for an exciting and informative session. First off, just a quick word about Kolena. At Kolena, we're committed to this idea of advancing the quality of AI models through rigorous and systematic testing as the key. So our platform provides comprehensive tools for evaluating and refining machine learning models, ensuring that they perform reliably in real-world scenarios. That means from detailed performance metrics to robust evaluation frameworks, Kolena is helping AI teams build models that they can trust. And we're also having a conference coming up in just 2 weeks now. So we're excited to invite you to the AI Quality Conference on June 25th. It'll be in San Francisco. This is our first conference. It'll be a fantastic opportunity to dive deeper into AI quality and connect with industry experts. We have a stellar lineup of speakers from companies like OpenAI and Google, Weights and Biases, lots more. Really looking forward to the event. If you stick around to the end of the webinar, I'll have a discount code for you to use if you'd like to attend. All right. So without further ado, let me give you a quick intro to what we're going to talk about, and then I'll hand it over to Saad. So metadata, what we're here to talk about, is the data that describes your data. It's the key to stratifying your test data, and therefore the key to robust model performance. The presentation is going to give you a comprehensive overview of using metadata for scenario-based testing, metadata across different modalities, and metadata extraction techniques. Please give us your questions. There's a Q&A function here in the Zoom. Go ahead and drop your questions in there. We'll answer them in written form, and then we can also answer some of them live at the end of the talk. But please put those in throughout so that we have those ready to go and we can get those answered for you. Whenever you have something pop into mind, drop it in the Q&A. All right. And again, very excited to have Saad here with us today to talk about his findings and practical guidance for using metadata. I'm going to go ahead and hand it over to Saad now. Welcome, Saad.
Thanks, Skip. So hello, everybody. I'm Saad Hossain, and let's just share my screen. So a little bit about me. So I'm an engineering student at the University of Waterloo. And I have a good deal of experience working at a number of different startups for that deal with machine learning problems, such as IntelliSports, where I built machine learning models for human activity recognition based on kinetic sensors. I also spent a good deal of time at DeepBreathe, which does a lot of medical imaging using lung ultrasound. And I developed some of their AI models as well as a good deal of their infrastructure. And now here I am at Kolena, where I'm looking to enhance the way we test models and ensure that we have the latest cutting edge practices in that. In terms of some of my research work and my research focuses, I've published in a number of workshops and conferences such as NeurIPS, ICLR, CVPR, and KDDF, co-authored, in multiple workshops and conferences in fields of domain adaptation, pose estimation, and defect detection. So let's talk to you about how that translates over to enhancing the way we test AI models and how we use metadata to do that. So a quick run through over what I'm looking to go over in this presentation and this webinar. First, I'd like to start off with defining what metadata is, how it's used in machine learning, why is it important, a little bit of a background behind it, and then I'd like to move on into how that relates to potent testing, how it relates to scenario-based testing, how we want to fill our holes using metadata. And then I'd like to get to the crux of the talk, which is how we extract this metadata for various different machine learning modalities, such as natural language processing, computer vision, audio, and more. And then I'd like to top that all off with a demonstration of how this would look in the real world and how you'd perhaps use this in your projects. And then hopefully we'll have some time for a little bit of a Q&A. So start off with, what is metadata? So as the name would suggest, metadata is data that provides information about other data. It's effectively data on data, right? And this information or this metadata can be of many types. It can pertain to the collection, to information relating to the collection of the data. It could be relating to the description of the data or even the structure of the data. And essentially any facet in which the information is related, any way in which we can describe it or ascribe any properties to it, any information relating to that would be and can be considered metadata. Now, metadata itself is supplemental in nature, right? So it is the descriptive characteristics. It's like an adverb it's like an adverb, right? It's not the verb itself, but it's something more descriptive in nature. And now, why is metadata exactly so important? Now, metadata itself can be used for a number of things, right? It can be used to enable very strong and rigorous data analysis as well as information retrieval. It's been used for quite some time now in information sciences and library sciences. It's the very reason why you can go to a library and you can kind of very easily navigate the library. You're able to choose the books you want. You're able to go through and find the books you want, right? It's the very reason when you look up a country and you see the population, you're able to see its breakdown. You're able to see how many, you're able to see the breakdown by race, gender, age, occupation. You're able to see all these wonderful things because with every data record, there's a lot of metadata associated with that. In a machine learning context, when we look at a data set, or even a scientific or engineering context, when we look at data, when we look at a data set and we have rich metadata, we're able to detect outliers or biases and have a more comprehensive understanding of our data. And we're able to, look at it more holistically and understand it to a better degree. And that is effectively why a lot of regulatory bodies and a lot of governing bodies generally want metadata. They like to see metadata. They're big fans of it. As we know, the FDA, especially, whenever they run through any clinical trials, they like to see good test coverage. They like to see that you have tested in all the different relevant scenarios. They like to see that you've thought through this problem, that whatever experiments you're running or whatever trials you're running, they're comprehensive and that you've covered your bases, right? And a good example for this and a big reason why a lot of us engineers, we study a lot of these failure cases and these case studies on engineering failures. And unfortunately, there was a very famous case of a drug which was thankfully not approved by the FDA, but unfortunately it did go through in Europe, and they did not test they did not test the drug's efficacy on pregnant people, and it did in fact lead to catastrophic effects, which really drives the point home as to why having strong test coverage and having a strong understanding of how representative your data is, how valuable and how important that is in driving any deployment decisions, in any engineering decisions, in any design decisions. And yeah, so I think it goes without saying that metadata can be and is quite an important factor in engineering processes, especially in AI. Now, how does that tie into exactly scenario-based testing? Well, if you want to define various different scenarios, as you can imagine, you will in fact need metadata, right? Because you need some sort of information that describes your data, some sort of information that's able to tell or define the scenarios as well. For example, if you have an image, you'd like to know if that image, what type of image is it? Perhaps you could look at its color, you could look at its you can look at its blurriness. You can look at a number of different characteristics, which may or may not be of critical importance based on how prevalent it is in your problem space, based on what risk is associated with it. Not all types of failures are as catastrophic, right? So really understanding that and understanding how that ties into your model's performance is something that is extremely key. And also knowing whether you have sufficient information to even drive a conclusion is something that metadata definitely enables and something that it allows, and why we would look to having very meaningful and rich metadata. So now that we understand why metadata is important, we have to understand generally where metadata comes from. So this information or this data generally does come from some sort of information processing system. Now, this could be the operating system of your computer. If we were to take a file, for example, right? When we look at a file and we look at what quote unquote metadata is associated with it, we see the file extension. It could be a .png file, which would mean that it's an image. It could be a .mp4 file, which means it's a video. It could be a .mp3 file, which means it's an audio file. We also know that it comes with the size, whether it's 450 kilobytes or a gigabyte, what type of access or restriction policies these are. So the computer itself is able to extract all of that and define a lot of that, and we can have that as the proxy for our information processing system. But now when it comes to machine learning, we would also use this, we would any data for which we'd like to generate metadata, we need to process it through some sort of an information processing system. And when it comes to machine learning, these are generally labeling tools, right? We label and we categorize our data. We ascribe labels to them. We say that, oh, this is a male. Let's say we're looking at, a cat versus dog, classic example in machine learning. We have a cat versus dog classifier. We know that we can have the breed of the cat and we can have the breed of the dog. We can have the age, gender, and we can use this to have a more comprehensive understanding of our data. And this would all either be labeled perhaps by a gene expert or even processed by some computer that would be able to automatically extract this. Now the problem comes by, and the problem, we all know why metadata is very important, but what if there's no metadata? What if it was not very rigorously labeled and categorized into all these assortments? What if we don't have, timestamps? What if we don't? Well, what if we did not do all this rigorous record keeping? Does that mean that we cannot have a very comprehensive scenario-based testing evaluation? Not necessarily. As we know, what we do need is an information processing system. This can come in various shapes and forms. Obviously, we are limited to some degree in the types of metadata we can extract. It might be a bit more difficult to get temporal metadata on what time of the day an audio file was produced. But some other things like whether you're looking at a male or a female in a picture, that might be a little bit more easy to prescribe. Yeah. And now moving on to how exactly we can extract this metadata, especially if it has not been subjected to extraneous manual annotation. It's very possible that the only metadata is the X and the Y, the label that you have. Now, as mentioned before, it is still difficult to obtain certain types of metadata. However, it is very much possible to obtain metadata that is more descriptive in nature, right? So when we look at an image or we look at a paragraph or a sentence or a text, we're able to effectively describe it. We're able to use various different number of tools to give or to ascribe a number of properties to it. And this can be done generally through traditional feature engineering and extraction techniques, or we can even leverage more modern AI-based systems such as large language models and open vocabulary models, language vision models, and all these different very interesting and impressive developments in AI. And we can actually leverage those to extract very potent metadata. And this could be metadata that is generally applicable. And actually, in the next couple of slides, I'll actually go through a number of essentially properties that we can extract that should be invariant to most machine learning problems in that modality, but also appreciating that there may be the need for very more fine-grained custom solutions, which can actually be facilitated by these new state-of-the-art models. And we know that this is a very highly active area of research. So these boundaries and these limitations could be being pushed I guess, as we speak. Now, I'd like to move on and talk a little bit about extracting metadata in natural language processing problems. So in front of me, I have a list of properties that we're actually able to extract on the Kolena platform. And these are fairly comprehensive in the sense that they are generally applicable to most most natural language processing problems. So as you can see, there's kind of chunks, and I'd like to go into more detail into each and every, maybe not each and every one of these, but certainly the main categories of relevance. So for example, the first category we would have is the standard properties that perhaps you could consider a bit trivial, right? Like things like character count, word count, and sentence count, which are fairly easy, with a couple of lines of code in Python, right? You could easily gauge how many characters there are in a text. You could also gauge how many words and how many sentences there are. But these speak to more intrinsic properties of your data. For example, we're all aware that a lot of models or AI models in natural language processing have what we know as context windows, right? They may be limited in the amount of text that they can take in, right? It might be 4,000 tokens, it might be 8,000 tokens, there might be a certain word limit, and it might be detrimental to the model's performance if we have a sufficiently large amount of characters or a sufficiently large amount of text. It might actually be detrimental to the model, or in certain scenarios, it might actually be beneficial in the sense that we're able to provide more information as opposed to smaller information. It can also tell us about perhaps if we're not using machine learning and we have a certain type of pre-processing step where we look to chunk certain texts into multiple different segments, we can see how the different variety of character counts, or the different sizes of character counts and word counts and sentence counts and length of text, how that varies in our system based on certain system characteristics or certain model characteristics, which can help us debug certain properties. Maybe you need to increase the context window, use a larger model, or maybe you don't need to. Maybe it's invariant and you can try experimenting with smaller models. Now, outside of these very standard properties, we also have more feature-based properties in NLP, right? Now, readability is something that's actually been studied for quite a bit in terms of how readable a text is. There's actually a toolkit called TextStat, which does a lot of nice work on this and has implementations for various different definitions of this readability metric, right? So over here, the way that this specific readability metric is standardized or defined is by grade levels, right? So you have fourth grade and below, you have fourth grade to eighth grade, essentially simulating or emulating the school system, right? And matching that to how a text might be perceived. So for example, a text or a sentence such as saying, "No, I'm your father," would be fourth grade and below because it's fairly lightweight or easy vocabulary, whereas something like Lindenstrauss, which I hope I pronounced correctly, would be of 16th grade and above because it alone is a difficult word, right? Now, some similar fields to this would actually be the count of difficult words, the number of misspelled words, as well as the number of named entities in the text, in addition to a lot more. And what these enable is understanding how your model does in various different scenarios, appreciating that we might be able to assort readability as a proxy for the difficulty of a text. We can use this to assess how our model performs in different scenarios, right? How is it performing for for individuals or texts that are catered to people below eighth grade or to people above the eighth grade, and understand how our model behaves and performs in these various different scenarios. And this is something that is fairly extractable. Now, outside of these more feature-based properties and these very standard and well-defined properties, we also have model-based properties such as sentiment subjectivity, polarity, the emotion, what topic a text is talking about. And these are model-based, so they do carry a degree of uncertainty to them because AI models are, at the end of the day, they are not perfect. However, they are quite insightful in the sense that they do provide salient signals. So over here, if you look at something like subjectivity, especially if you're looking at a task like question and answering, sentiment subjectivity can tell you how opinionated a question is, which might actually be a proxy for how difficult a question is, right? A question like magic mirror on the wall, who's the first of them all, would have a fairly subjective tone to it, whereas watermelon seeds passed through your digestive systems would be a more objective statement. And we can use the properties like this, like sentiment polarity, like the polarity, or how emotion, or the emotion that a text might carry. We can use these properties to further our understanding of our data and enrich it with more scenarios to test on, to see how our model performs on these. Are these of importance to your problem space? And we can use these to essentially have a more enhanced testing experience, and basically obtain additional trust in our model deployment decisions. Now, if we look at, I guess, essentially more examples, like a sentence like the woman is cutting cooked octopus, right? So it is intuitive to understand. Perhaps someone in the fourth to eighth grade would be able to read it with fair ease. We understand that a topic tag can be associated with it, and we see how this, like, we go from having a sentence, which essentially that's all it is, right? It's just one piece of data, and now we have all these associated properties with it, some of which I've discussed in the previous slides. Now, what if our data was not human readable? So all these examples seem quite well and seem quite nice if it in fact does pertain to something human readable, some natural language. What if it's a piece of code? Like what we have here, we have some SQL code on the screen, and we appreciate that something like readability might not be the most applicable here, as well as something like emotion might not be the most applicable here. So we do understand that there might be need for some more custom metadata. And that's actually where LLMs or large language models like GPT, like Llama, like Claude, where they can actually be quite useful and quite insightful. So for example, over here, we have a query, we can pass it through into a large language model with some nice prompt engineering and a good, well-structured prompt. And we can actually find the type of query it is, as well as the subject. And in addition to obtaining the metadata, we know that it's a single join, and we know that the subject is analytics and reporting. We can also look to obtain the reasoning as to why this data point, or this piece of essentially text, or this SQL query, why it was assorted into these categories, why it was given this query type, and why it was given this subject. This reasoning can also be obtained, which allows us to obtain more insight and more essentially more transparency into the thinking, which may or may not be correct. But the point is that we can assess and we can look at it for ourselves, and we can try to extract all different types of metadata using LLMs. Yeah, and they are fairly good at that because they have been trained on significantly large corpus of information. Now, moving on to computer vision, we've gone through a lot of very interesting examples in the field of NLP, where we have these large language models, and we have this very well-defined, essentially, a history of information sciences behind NLP. People have been looking towards, a sorting thing. Library sciences has been a field that far predates modern AI and machine learning. So how would we look to extract similar metadata for computer vision problems? Now, this is now in front of us, we actually have an image from the ADE20K dataset, which seems to be in some sort of a highway. We see a car, and I'm not sure exactly where it originates from, but in front of us, what we might see is just a picture. We actually understand that there are a number of ways in which we can describe this image that would actually enable us to have further understanding, because this would only be one of many pictures in the data set, right? And if you want holistic understanding, there are certain properties that we can look to extract. For example, over here, we've actually extracted the dominant color, which seems apparent to be blue. We also know that it is fairly symmetrical. Actually, we have a good symmetry score, and as you can see, yeah, there's not much difference between the two halves of the image, especially if we look at it from a vertical sense. We're also able to extract the sharpness of an image, which essentially tells us how many edges there might be, how blurry an image is, or how sharp an image is, the number of essentially how detailed an image can be would be defined by a property such as sharpness. Now, a property such as pixel entropy over here, we have fairly high score, would essentially tell us what's going on in the image. Is it just a very bland or blank image where there's not many colors, where there's not many objects? Something like entropy, which generally is known to detail the amount of chaos or uncertainty in some signal. This could, in fact, tell us how chaotic an image is and how much is going on. The more that's going on, the more chaos the more entropy it has. Things like contrast, brightness, aspect ratio, width, and height. These are very standard, and a lot of these, at least width, height, and aspect ratio, can actually oftentimes be extracted from your file processing system as well. Alone, we see resolution from it, and a lot of these are very intrinsic properties that we can look and we can have further understanding of. Now, interestingly enough, as as previously known, this might not encompass all the needs one might have when looking to extract metadata, especially in computer vision problems. We might also want more custom metadata. We might want to classify this image into a number of different categories. So this, in fact, is an airborne object detection problem. And for something like this, you might want to know what landscape we're looking at. Is the airborne object, is this helicopter in a water body? Is it in mountains? Is it in a farmland? What is exactly the background terrain? We might also want to know how cloudy the sky is to understand how our machine learning model performs in different weather conditions. And the developments in language vision models, in open vocabulary classification systems, in zero-shot object detection, zero-shot classification systems, the research that's been currently poured into that and the advancements in that really enable and allow for this, appreciating that there is a degree of uncertainty that follows the extraction of these features. Now, not only can we extract metadata from the image alone and from and just using LLMs in terms of classifying it, we can actually use annotations themselves to further our understanding of a certain image without having to explicitly look at this image. So when you're first given this image, you might just have a series of bounding boxes, and effectively what you just have is a number of XY coordinates without much more to go on. However, there's a lot that can be extracted from just the presence of these bounding boxes. You can also understand how congested an image might be based on the number of objects in that image and how close they are in proximity. So a little bit of bounding box analysis can enable these essentially features and properties. So we have things like congestion to see how squeezed in. We see that congestion is pretty high in this image, especially with all these trucks side by side overlapping each other to a good degree. Also, we can measure the amount of spread and see how spread out the objects are, especially the objects of interest. We can count how many objects there are. We can see how far they are from the center as a proxy to the locality of a certain object or the objects in general. We can do all sorts of analysis that may lead to potential insights in our data. Now, we're not just limited to NLP problems and computer vision problems. In the field of audio processing, there's actually a lot we can do based on traditional signal processing methods, as well as just transcribing audio and doing the same thing we did before with text and treating it as a text problem. So over here, we see that we have energy, which is essentially the power of the signal. We also see how long the signal is, the sex of the speaker, as well as things like pitch and tempo, which are more specific to audio and can help us understand our audio data set better. But we can also extract text features from the transcription, a lot of which we went over before. Now, interestingly enough, this methodology can virtually extend to any sort of annotation or essentially machine learning modality, right? Even if we look at 3D annotations, if you look at a point cloud, there's a number of essentially geometric analyses that can be done. We can calculate the density of points. We can calculate the separation of points. We can also calculate the roughness as well, which perhaps could be a proxy to understanding what terrain we are, especially in the context of autonomous vehicles. And yeah, there's essentially and there's effectively a lot that we could extract and that we could essentially obtain just from the presence of annotations alone, as well as using a lot of the latest and greatest technologies. Now that I've kind of gone over all of these various different metadata or properties or features that we could directly extract, what does this look like in the real world? What does this look like in the context of an actual machine learning problem, right? How can this be used? We'd actually like to go to Kolena and show what this looks like. So over here, I'd like to demo essentially how metadata hydration might actually improve testing quality. So right over here in front of us, we are looking at the Kolena platform, which is, as Skip mentioned before, an AI testing platform that enables rigorous machine learning testing and also facilitates fine-grained debugging of models and accelerates deployment decisions. And essentially a quick run through over some of the key functionalities would be the fact that we can go to the studio and look through our data and see essentially what our data looks like. We can see what our model results look like. We can then go to the distributions tab and we can see how our we can see the various different distributions of the different fields. And then we can go to the debugger and we can stratify by these different properties and these different fields that we have, and we can plot them against each other. We can plot different properties and different results against each other to perhaps understand our data more. And we can have confusion matrices. We can have all sorts of different plots, and then we can go to the quality standards page and we can see how our model performs in the various different scenarios that we have defined. We can also compare models and can do all sorts of interesting and fun things. Now, going back to what type of data set exactly we're looking at, or what type of machine learning problem this demonstration is about, we're looking at visual question and answering. So in this problem, in the problem of visual question and answering, what we are given is, or what the machine learning system is given, we're given an image and we're given a question. And that question will generally pertain to the image itself. And we want a response based on the information that is present in this image. So for example, over here, an example question would be, what is the color of the bear? And some acceptable answers would be black and brown. Excuse me. And yeah, that's effectively the problem. And when we look at it through the studio, we see over here, a question for this would be, are there adults at the table? What the responses are. Now, this is an open source data set, the VQA V2 data set. And if you were to just take it off of Hugging Face or whatever platform it's hosted on, what you might see, in fact, uh, is something like this. See, you have your questions, you have your responses, but that might basically be all that you have. You just have your X and your Y, and there's not much you can really do. All you can do is you can figure out the aggregate accuracy, but that's all you know. You don't really know you don't know how it performs on more difficult or easier questions. You don't know how it performs on blurry images. There's not really much you know about how your model performs. Let's say you get an 85% accuracy. You don't really understand, you don't really have full understanding of what that means. So if you go through the distributions tab, this is all you know. You have your answer, and you have your question. But when you hydrate it using some of the extraction techniques that we went over previously, we can now see the distribution of blurriness in our data set. We can also see the diversity of color. And actually, if we inspect and if we see the diversity, we actually see that most of our images are in fact to some degree blurry compared to the rest, where there seems to be less representation of these buckets. Now, if we look at something like color diversity, we actually see that it's distributed quite nicely. It's a nice bell curve or normally distributed property, and so we know that we have a good diversity or variance in the color in this specific property, and we're able to see that. We can then go on to different properties, and we can see essentially if they're well distributed, we see that we don't have that many negatively connotated or negative questions. Most of our questions seem to be either neutral or slightly positive. We also know that most of our questions are objective. So perhaps one thing we might want to look to do after we've seen something like this is maybe we need more samples. Maybe we need more very subjective samples. Maybe we'll understand how our model performs on very objective texts, but we might not know how our model performs on more subjective texts. So that's something an extraction might, well, that's an example of an insight an extraction might effectively tell us. We also might be able to extract the topic, and going through the studio, really looking through the platform, we're able to see, for a data point like this, are there any adults at the table? You have this hydrated metadata compared to what we effectively had before, which was just the question responses and maybe a little bit about the type of question. So we're able to assort through it. We're able to see what type of question it is, what does it pertain to? And yeah, so for example, over here, we have the answer is, bedroom or hospital. So we know that the topic of this question is the location. We also understand, the subjectivity of the question. This is a fairly subjective question, which is why we have multiple different answers for it. So once we're able to extract all these different features, we're able to have a better understanding, and we're able to perform more analyses, and we're able to effectively do more rigorous testing. And what we can actually do now that we have all these different properties, we can introduce our model results and see how that can correspond or be related to such. So we've added results from the Velt model, and just going off the results quickly, we can see holistically the accuracy is 87.95%. And if we were to remove this, if we had effectively no metadata, that's all we would know. We wouldn't know much more than this one number. But if we were to stratify by something such as, something like color diversity, what we would be able to do is we'd be able to see how our system performs, on images with low color diversity or with high color diversity, and we actually see that there seems to be a trend. And we can actually look to plot this. So if we were to look at something like color diversity, and then if we were to plot the accuracy of the model hand in hand or beside it, let's say we could look at the mean of these values. Again, with this, we actually see that there seems to be a general decrease and then a large increase. And that is perhaps something we can look to investigate further. There seems to be quite a large jump, especially in this bucket. And these are the analyses essentially we're able to do. One other interesting thing we can actually do once we've extracted all these various different metadata types is we can look at the distribution of our failures. So we can look at samples which have very low accuracy. We can then apply these filters. And we can see for blur level, it seems to quite aptly match the distribution, the original distribution. So just for context, the green is the distribution of the failures, and the purple is our original data sets distributions. We can then go on to color diversity, and we can see that there is a very slight difference between the right half and the left half of this distribution. We actually see that the green bars are lower than the purple bars, indicating that there seems to be a lower proportion of failures in test samples in which we have lower color diversity, whereas there's a higher proportion of failure for images where we have a higher color diversity. We can then do the same type of analyses on various different properties. We see that this is extremely emphasized in character count, where we see for lower character counts, we actually have lower error proportions, but for high character count, we see that quite significantly increasing, especially in these two bins. And once we see that, perhaps one thing we can do, at least for color diversity, actually, like just going back to that property, we can look at something like this perhaps, and we can click on it and we can apply this filter. And once we've applied these filter, we can manually go through the studio and we can see what this means. So we can see for this, I guess, essentially increased color diversity, what does it mean? What type of samples are we generally looking at? So over here, we actually see the accuracy is 0. So this is essentially an example of an error. And we see the inference is store, and we're able to inspect our failures a bit more intensely on these more diverse images. Conversely, we are also able to see images with lower color diversity and how we perform on those. So again, over here, we're doing particularly perhaps a bit better on these. Yeah, you see there's a lot less color diversity here, perhaps a lower proportion of errors as well. Now that we see now that we have a feel for the properties that might be relevant, we can actually go to our quality standards and we can define it. So we already know about metadata. We already know about color diversity. We can also add something like character count. And we can save this. And then we can now view our model results and see how it performs on different character counts. And we see that in the 4th quartile, actually, there seems to be quite significantly worse performance. So now we can understand that our model performs worse, and perhaps we need to upsample this scenario in our testing. We can add more examples of this. We can train some low-hanging fruit. Perhaps we can add augmentations to increase the size of text and increase the context window of our models. And there's a number of things we can do once we're informed by these decisions. Another thing that we can see is we seem to be performing quite poorly on numeric questions, and which is further highlighted over here, whereas we do quite good in yes or no questions. So from these extractions, we're able to understand some of the failure points of our models, some of the areas in which they perform worse. Moreover, we can also we can also compare various different models, and we can essentially ease the process of making deployment decisions. So for example, over here, we notice that this Wilt model seems to be better than the Blip model on effectively all the metrics. If we actually lower the significance score a little bit, we do notice that there's a slight regression in yes or no questions by about a percentage point. But we also notice that overall it seems to be better in every different scenario. So if we value yes or no questions a lot more, then we might reconsider the decision to deploy Wilt. But if we value it equally as to other properties, we may consider, or we may have a more easier discussion in deciding whether to deploy the Wilt model or the Blip model. Now that I've showed you some of the features and how you could perhaps use extracted metadata to enhance your testing, I'd like to show or highlight some of the other metadata extractions that we could use in the real world. For example, we have this semantic textual similarity benchmark where we're able to essentially compare how semantically similar two texts are. In the Kolena platform, actually, we're able to extract these various different types of metadatas. So if we were to just look at an example quickly, and you're looking at this sentence, South Korea declares end to MERS outbreak, and you want to know what emotion carries or what emotional connotations are associated with the sentences in this data set, you can then go and configure this text extraction. You can add the emotion tag. You can then save this configuration. You can click and you can see, all right, the emotion seems to be fairly neutral. There doesn't seem to be anything outstanding. You can then go to distributions and you can check and see how distributed it is. And you can perhaps have a little bit more understanding of the different processes in your data set. Similarly, just going over how some of the image properties look like in the real world. If you were to sort by something like sharpness, you can see how these are very detailed images that have very high sharpness. There's a lot of leaves, a lot of detail. And if we were to sort in a decreasing manner, we'd see that these are a lot more bland images. So once our model does once we do evaluations stratifying by these properties and we identify failures, we can perhaps be informed more of the different augmentations that can be used perhaps to enhance your model performance. Similarly, just looking a little bit at the bounding box properties or the object level properties and what that could reveal in our evaluations. We can sort by these different properties. You can see that if we're looking at a property like congestion, we see these images are a lot more congested and there's a lot more going on in these images. There's a lot of objects very close to each other. Whereas if we were to sort by that in decreasing order, we'd see these are a lot more calm images. There's only one bus, there's only one truck, there's only one bike, and there's not much else going on. So we know that these are perhaps more easier examples, and we might be able to choose certain augmentations or upsample data, especially if we see different performances. But yeah, that essentially was a little bit of a demonstration into the world of extracting metadata, essentially going from zero metadata to essentially a bunch of different metadata and furthering your understanding of model and having more enhanced evaluations. And yeah, with that, I'd like to move on to the Q&A and pass it back to Skip.
Thank you very much, Saad. Let me go ahead and share my screen. Cool. Yeah, we've got a little bit of time left for Q&A. If you've got any questions for Saad, or if you've got things you're wondering about in terms of how you're using metadata for your own projects, we'd love to have that come through. We just have a few minutes. While we're waiting for that, Saad, I do have an initial question for you here. And this has to do with using metadata for interpreting and explaining models. I'm wondering how you see metadata being a factor in terms of explaining and interpreting how these models work.
No, absolutely. I think metadata is extremely relevant in this. We also know, and this is a fairly hot topic in AI research, the idea of fairness. It's actually becoming more and more increasingly popular, and we know that regulatory bodies like seeing the idea of fairness in models where various different subsets are in fact represented and incorporated as an optimization objective when you're developing your machine learning models. So it's definitely something that can heavily influence the interpretability and explainability of machine learning models. You're able to understand how your model behaves a bit better, especially if you're looking at, yeah, your model is failing when we're looking at very large text samples or we're looking at very small text samples. We're able to understand the model's performances a little bit. Perhaps we're able to understand its biases if it tends to ascribe a certain prediction to a certain group at a higher rate than others, then that would be indicative of a model's some of the model's behaviors that would in turn explain some of its behaviors and characteristics.
Yeah, makes sense. And to me, metadata is essential if you want to demonstrate that you're testing against a particular class of a problem, and you want to demonstrate that you're getting robust performance or that you're handling it safely, whatever it is, then metadata is the way that you're going to narrow down and start to specify that. Great. Thank you very much. Here's a question for you. Let's see. Are you seeing this in your interface there?
Yep.
It says, can you refer to a paper where metadata has been successfully leveraged to enhance performance? I'm not sure if you're aware of that.
Yeah. So there's definitely several papers. This is even if we look at the presence of TinyML, or when we're looking at even the YOLO models, which are very popular in AI and machine learning, and when we look at their performance in larger objects versus smaller objects, we see that we try to incorporate, and there have been papers on scale invariant machine learning models where essentially you look to have anchors of different sizes to essentially target smaller objects and images. That's just one example. And in generally, the practice of upsampling or using sample weights is something that's heavily prevalent in the machine learning space. It's a fairly it's a fairly used and prevalent tactic in terms of targeting label distribution imparities, where a certain class might be underrepresented, upsampling that or using augmentations to generate that to improve performance. There's definitely a lot of papers, and perhaps even if they may not be targeting the subject of metadata extraction directly, these are in fact properties that very well can be extracted and then used in turn, to use in further developing your models.
Right. Another question for you. Just thinking top level, what comes to mind? What are the common challenges or pitfalls that teams are likely to encounter with metadata in terms of just any kind of machine learning project?
Well, one of the common pitfalls that I believe a lot of people generally tend to have is to obviously have meaningful metadata that successfully represents their data set or successfully represents the population of the population of essentially their deployment, right? When they look at deploying their model, are they able to hit every single test case or at least the extremely important ones and how that's defined? And that really does often need a good amount of effort into understanding what scenarios we're looking for, what metadatas might be relevant in informing these scenarios, what populations are informant. It really starts with understanding what scenarios you need to test for and how you can enable the essentially the assortment of your data into these various different scenarios.
Right, exactly. Great. Cool. Well, we're running out of time, so just very quickly, what do you see as how this field is going to develop? Obviously, we've got the ability to automatically extract metadata, but where do you see this going over the next several years? How do you see this technique getting more advanced?
Yeah, I definitely think that the presence of open vocabulary models, things like idea research's grounding Dino 1.5, and even like GPT-4o, and some of the language vision models we have, in which you can just ask or prompt a system to describe an image in great detail, or even generate an image in great detail. It's able to very aptly and very accurately, oftentimes, describe an image. And I think that will allow for more essentially potent auto labeling, and essentially will ease in the labeling process. So earlier, when we would need more metadata, we'd probably have some labeler, do labeling, and now we can probably outsource that to machine learning models.
Right. Yeah. Yeah, definitely a very fast changing field, and I'm excited to see how things go. All right. I want to just give a quick summary to wrap things up here since we're just about at time. Thank you very much, Saad, for an excellent presentation, chock full of great info. Really appreciate your time. So just to recap very quickly, metadata, obviously just data that describes your data. It's used to enhance the analysis of your data, managing your data, and ultimately your model performance. It really enables potent testing. So utilizing diverse metadata enables these scenario-based tests that we're talking about. This is going to help you uncover edge cases and improve your model robustness. When it comes to automatic extraction, or hydration as we're calling it, there are tools and techniques for automated extraction in all the domains that we looked at: NLP, computer vision, audio, etc. Kolena can automatically extract metadata relevant to the data type you're working with, and that'll give you kind of a jump start on whatever data you're working with to get some relevant metadata to start if you don't have any, or even if you do. Key takeaway, though, is that metadata will significantly boost your model quality if you're making proper use of it. And it's essential for some of these more advanced ML evaluation practices, and excellent as well for demonstrating regulatory compliance. There's some further resources for you here. We have a lot of relevant resources for you on our blog. We have a metrics glossary, a fantastic comprehensive metrics glossary that our research team has been compiling over time. There's metrics on all different types of problems that you might be working with. Some more information on how we do our automated text metadata extraction here at this link as well, also in our documentation. And then check out our blog for lots of thought leadership and guidance about AI quality and proper testing and evaluation from the whole Kolena team. Last thing I'll mention before I let you go is just, again, we're having this AI quality conference. It's our first conference. We're really excited about it. It's coming up in just a couple of weeks here. I've put in this discount code for you here. You can get 75% off the ticket price. Just use the code metadata when you're registering. We'd love to see you here in San Francisco. And if you do sign up, please come say hi. Thank you all for attending. Thank you again, Saad, for a great presentation, and we will see you next time.